this is our third part for DC analysis. So let's have a review. The second part for DC analysis is we discuss the different configurations, and we have established that the most stable among those four configurations that we have discussed is the voltage divider circuit. Okay, so we have discussed the fixed bias configuration or the fixed bias circuit. We have discussed the emitter stabilized. We have discussed the voltage divider, and lastly, we have the collector feedback, the DC bias feedback. Okay, so aside from those four usual configurations, there are other type of circuits that you might be encountering. So for today, we will just discuss that even though there is a slight difference in the circuit, the approach will still be the same. So let us start with the so this will be called the miscellaneous bias configuration. So we will be starting with the collector feedback with its emitter resistance equivalent to 0 ohms. So if you're going to go back to our last circuit, which is the DC bias or the DC feedback configuration, it looks like your circuit here. The only thing that is missing is your emitter resistor. So what will happen if we have this type of circuit? So the approach is the same. So we will compute for the base current, and then from the base current we will be defining the collector current, and then finally we will be solving for the VCE or the collector to emitter voltage. So in this case, the only missing is the emitter resistor. So from the formula that we have derived last time, from the last formula that we have derived last time, this is supposedly beta multiplied by RC plus RE. But since we have a zero emitter resistance, we just drop your RE. So instead of beta multiplied by RC plus RE, we just have here your RC instead. Okay, so after solving for IB, we will be using this relationship between your base current and your collector current with your beta. So this is your IC, which is IC is equivalent to beta multiplied by your IB. And then lastly, if you will remember last time, so this is VCC minus you have your IC multiplied by RC plus RE. But since our RE is equal to 0, so what happens now is we just have here IC multiplied by RC. So that is the only difference. Okay, so if you encounter this type of circuit, so the procedure is just the same. All you have to do is to drop your RE since we have shorted your emitter terminal. Okay, so another type of configuration that we have is this one. Okay, so we have here if you're going to look at the circuit, the applied voltage now is connected to the emitter leg, while your collector is the one which is grounded. So the usual circuit that we have is that your VCC is connected to your collector. So you might be wondering, is this a common collector configuration? Is this not anymore a common emitter one? So this is still under common emitter configuration. Okay, so instead of VCC, we placed your supply at the emitter terminal. So if you might be wondering why we have a negative source at your terminal, so because that is an NPN type of transistor. So from the N type, we will be placing your negative terminal. So to make your input side forward bias. So that is our main concern, to make your input side forward bias. So the input side here is the base, because the source will be from the emitter, so that it will be providing a base current. Okay, so if we're going to redraw the circuit, so that you can understand how you're going to derive the formula, we will be redrawing your circuit. So I have here the redrawn circuit. Okay, so this is called the applied voltage, which is connected to the emitter leg instead of the collector leg. From the input side, you can see that we're going to have your KVL here. Okay, so since the source is written as negative, so that means the negative terminal, or the shorter symbol for your voltage source is the one which is connected to your emitter terminal. So it is minus plus here. Okay, so negative, positive. So we will be calling that VEE. So not VCC, because when we say VCC, that is one which is connected to the collector side. So if it is connected to the emitter side, we will be calling it your VEE. So we have here your VEE connected to your RB, okay? And then we still have here your positive and your minus negative VBE. So if we're going to have a loop here, we're going to have your KVL here. So that will become, so exiting your base resistance. So that will be minus IB multiplied by RB. So we have here minus negative VBE. So we have here plus VEE is equal to 0. So we can solve for IB. So what is IB? IB is VEE minus VBE divided by RB. So this is just, it looks familiar. So the only difference is, instead of VCC here, we are going to make use of VEE. Okay, so you don't need to memorize the formula. Just look at how we derived it. Okay, so because if you're going to memorize it, if the circuit happens to look different, you might be confused. So you just have to learn how to derive your equations. Okay, so after solving for IB, still the same, we will be using your IB result in solving for your IC. And IC is still equivalent to beta multiplied by your IB. Okay, at the output side, what will be the difference? So the difference at the output side is your source is still at the emitter side. Okay, so if we will be following the configuration or the polarity of your source, so your current will be flowing from the negative to the positive of the source. So you have here your plus and minus RC. So since our RC is grounded, it is the one which is connected to the other terminal of your source, which happens to be the positive side or the positive polarity of your VEE. Okay, so we have here your IC. So upon entering RC, so we have a voltage drop here. So we have plus and minus. We still have your VCE here. So plus and minus VCE. So if we're going to apply KVL or Kirchhoff's voltage law at this loop, we will be having minus negative IC RC. You have minus VCE plus VEE is equal to 0. Okay, so what are we solving for? So we are solving for your VCE, and your VCE is equivalent to your VEE minus IC RC. So it is technically, it looks like your other formulas for VCE, but okay, the only difference is we used VEE instead of VCC. So why VEE? Because the source is located at the emitter leg instead of the collector leg. Okay, so that is the second miscellaneous configuration that we have. Okay, so we also have like this one. Okay, so this is what is the difference between this one and the previous one? Okay, so the previous one is that the collector is grounded. So if you're going to look at the collector, it is grounded. So the collector is grounded this time, but okay, so we cannot see the effect of the common collector, or also called the emitter follower, yet here because we are still under the DC configuration. But we're going to find out that using AC analysis, we will find out that emitter follower follows your input signal. Okay, so whatever your input signal is, whatever the polarity of your input signal is, that will be also the polarity of your output signal. And another thing is, it is not usually used as an amplifier because the output here is much lower than your input. Okay, so in an amplifier, your output must be higher than your input. But using the common collector configuration, or also called the emitter follower configuration, the output here is always smaller compared to the input signal. However, we cannot yet see this in this discussion because that will be discussed on the AC analysis part. So what are we going to do now is to again solve for its DC parameters. Okay, so the DC parameters is still your DC currents and your DC voltages. So what is the difference between this one and the one which has the source located at the emitter? So this is the same. So the difference is that where are we going to measure your output voltage? So in the previous example here, so the output is still measured across your collector. So the input is at your base and the output is at the collector side. So when your input is your base and your output is at the collector side, so you still have a common emitter configuration. So what is the difference is that our output here is being measured at the emitter terminal. Okay, so the input is your base and the output is at the emitter. So therefore, this is a common collector configuration. So the difference lies in where are we going to measure our output voltage. So in this case, so look at the previous one. The output is taken at the collector, while this one, the output is taken at the emitter. Although we cannot see the output yet, but that's the main difference. Okay, so what are we going to do here now is just to follow what we have, what we've been doing from the start. Okay, so in this case, again, let us take so this is your emitter follower or the common collector. So at the input side, look at the input side, we have your resistor RE here, we have your VEE here, again negative VEE, so the negative terminal is the one which is connected across your RE here, and then we still have your VBE here, and then the current flowing across your RB is your IB, and the current flowing across your RE is your IE. However, we're going to make use of this formula wherein IE is related to IB by beta plus 1. Okay, so applying KVL here, we have minus negative IBRB. So you have minus VBE minus IERE plus we have VEE is equal to 0. However, IE is beta plus 1 multiplied by IB. So, substituting that in the formula, we can solve for IB. So, what is IB? IB is VEE minus VBE divided by RB plus beta plus 1 multiplied by RE. So, is this formula familiar? So this formula looks familiar. So this is just the same as with the emitter stabilized configuration. The only difference is instead of VEE here, from the emitter stabilized configuration, we used VCC. But the remaining parameters in the formula, they are just the same. Okay, so for IC is still equivalent to beta multiplied by IB. And then at the output side, look at the output side, instead of VCC, you have here your VEE with the same polarity here. Okay, so you can either make use of IC, which is equivalent to IE, or we can say that more exact value, IE is also equal to beta plus 1 IB. So either of the two, you will just get a slight different answer, but it is acceptable. Okay, because in in uh, in BJT transistor, we always approximate IC be equal to your IE. But anyway, so substituting that in our formula, performing KVL here, you have a minus VCE. So you have minus beta plus 1 IB, okay, multiplied by what? I lack RE here. So you have here RE. Okay, so IB RE plus VEE is equal to 0. So the only thing that is unknown there is your VCE, and then VCE is equivalent to VEE minus beta plus 1 IB multiplied by RE. Or you can also write this as VEE minus, since IB is approximately IC, so this is approximately equal to IC multiplied by RE. So the only difference is instead of using VCC, we used VEE because the supply is located at the emitter line. Okay, so this is an example of a common collector configuration because the output here is taken at the emitter, while all of the other previous configurations that we have discussed, all of the outputs there will be taken from the collector terminal. Okay, so one thing that deviates from our common emitter configuration, aside from this emitter follower or common collector configuration, is the common base configuration. Okay, so this is your common base configuration. As you can see from the common base configuration, our input is taken at the emitter side. Look at the symbol. So our input is taken at the emitter side, and then our output is taken at the collector side. The one which is common here is your base. So the one which is grounded here is your base. So for the common base configuration, we usually have two sources. So we have your VEE here, okay, and then we have your VCC here. So we have VEE and we have VCC. So this is how your common base configuration looks like. So how are we going to analyze this? So the analysis is still the same. We're going to separate your input side and your output side. So the input side is between the emitter and the base, while the output side is between the collector and the base. Okay? So analyzing that, we have here So analyzing that, we will be analyzing first the input side. So the input side will look like this. So we have here your, since this is your base, so this is positive. Base is positive with respect to the emitter. So we have minus plus VBE. So following the polarity of your VEE, so you have minus plus. So the current is flowing from the negative going to the positive. So we have your plus minus. Since this is RE, the current flowing here is IE. So the difference between common base from the other configuration is that your input is the emitter current and not the base. So why not the base? Because base is the one which is common. So the input is the emitter and the output is the collector current. Okay? So in this case, applying KVL again. So we have here minus IERE. So we have here plus VEE. And then you have minus VBE is equal to 0. So instead of solving for IB, the input for common base is your IE. So we are solving for IE here. IE is equivalent to VEE minus VBE divided by RE. So this is just like your fixed bias configuration, but in the fixed bias configuration, this is IB and this is VCC and this is RB. Okay, so just like in the fixed bias configuration. And then from the output side, so the output side, IC is approximately equal to IE. So we have already solved for IE. So we will be using that as our IC. So from the output side, instead of VCE, so we don't have VCE here. Why? Because the one which is common is the base. So the output terminal or the output is being taken between the collector and the base. So since it is between the collector and the base, not between the collector and the emitter, so we will be calling that voltage VCB instead. So why VCB? Collector to base voltage. Okay, so with the polarity positive, positive, the collector is positive with respect to the base. So instead of VCE, so no VCE for common base configuration because the output is between the base and the collector. So applying KVL, we have minus VCC plus VCB minus ICRC is equal to 0. So VCB here is equivalent to VCC minus ICRC. Okay, so why IE here and why VCB here? Because our configuration is common base. Okay, so common base has only one variation. The circuit for common base is just like this one. So common emitter likewise, it has only one variation, which is the emitter follower. For common emitter, we have several. Okay, several variations of your circuit. So why we have several variations for common emitter? Because common emitter is the one which is being used as an amplifier. Another thing is this one with split supply. So this is just like your common voltage divider configuration. What is the difference? We call this split supply because we have two sources. Okay, so we have your positive VCC here and you have your negative VEE here. So the negative VEE, if you're going to notice, it is also connected with your R2. Okay, so what did we do in the voltage divider? We convert this part, so we Thevenize this portion of your circuit. VCC, R1, and R2, we Thevenize that. But, as you can see, your R2 is also connected across your VEE. So, in Thevenizing the circuit, your VEE here is included. Okay, so what will be the effect? So with split supply, the same procedure, we will still be needing to Thevenize your circuit. That means we need to solve for your ETH and we need to solve for your RTH. For the ETH, as you can see, you have two sources. Okay, so what are your two sources? Your VCC, which is directly connected across your R1, and then your negative VEE, so the negative polarity is connected across your R2. In solving for ETH, your ETH, we have here, this is not anymore in parallel with only your R2. So this is in parallel with this branch. And this branch consists of the voltage drop across R2. So ETH is, this consists of the voltage drop across R2 and your VEE here. So, but the polarity here is across R2, this is plus and minus, while your VEE here is minus plus. So, what happens when we have like that? So, it is not additive. So, your ETH is the voltage across R2, which happens to be the current flowing across R2 multiplied by R2. Then we have minus your VEE. Okay? So, what is the current flowing across your R2? So since this is an open circuit, this loop here becomes a series circuit. So this is simply equal to your VCC plus, so this is additive. We have plus VCC with the loop here, it will exit here, so plus VEE. So VCC plus VEE multiplied by the total resistance of your circuit. So the total resistance of your circuit is R1 plus R2. So whatever the voltage drop across here minus your VEE here, that will be your ATH. So for RTH, no problem. It will be the same because why? In getting the RTH, we kill the source. So how do you kill those two sources? We just short circuit it. So short circuiting your VCC here and also your VEE here, that will leave your R1 and your R2. So solving for RTH, what is the relationship between your R1 and R2? R1 and R2 are still in parallel with each other. So RTH is equivalent to R1 and R1 parallel R2. So just like what we did in the voltage divider configuration, we will be replacing the input side with the Thevenin's equivalent circuit. The Thevenin's equivalent circuit consists of your solved ETH here and your RTH here. So the difference again is we have your VEE here. Why? Because from the split supply, as you can see, your VEE is connected both at the emitter resistance and at across R2. So therefore, you can still see your VEE here. Okay? So, but anyway, that's not a problem. We just have to include that in our KVL. So, in our KVL, we just have your VEE here. So, you have VEE plus ETH minus IB RTH minus BBE minus beta plus 1 IB multiplied by your RE. So, the only difference from the voltage divider configuration is the appearance of your VEE here. So that is the effect of your split supply. Okay? So in the laboratory, how do you perform your split supply? So we have here, we have two inputs, right? In your voltage, in your power supply in the lab. So you have a two different voltages there. So you will be using those two. Okay? So that is how you're going to perform your split supply here. What are we going to do now is you're going to compute for IB. So this is just like the formula that you used in the common, in the voltage divider. The only difference is the appearance of your VEB. So upon solving for our IB, we can solve for IC. IC is beta IB. So at the output side, what will be the difference? So the difference again is your VEE is still there. Okay, so your VEE is still there. So in solving for your VCC, the only difference is your VEE here. Okay, so it's plus. That means your VEE adds up with your VCC. So by looking at the loop, you have here plus VEE plus VCC. So they will be adding up. Okay, so they will be aiding with each other. So the only difference is the plus VEE here. So the rest, it is the same. So you can still encounter different circuits. Okay, so we cannot discuss each one by one, but as you can see, the procedure is the same. Okay, so all you have to do is to separate the input side from the output side, and then you solve for the applicable input voltage. So almost all of the circuit that we have discussed, it is IB, and then you have to relate IB to IC. Aside from the common base configuration, because in the common base configuration we don't have IB, it's IE, and then you relate IE with IC. Okay, so even though you encounter problems or circuits that we haven't discussed, so you will just have to follow the procedures that we have done, and then everything is the same. Okay, so it is very simple. So, what is the difference when we have design operations? Okay, so what is the difference when we have design operations? So, what is the difference when you're solving design instead? Okay, so when you're doing design instead, this is one where the current and or the voltage may be specified, and the elements required to establish the designated levels must be determined. So the difference here, class, is that from the previous examples, from the previous derivations that we have done, usually all the circuit parameters, all the resistors are given. So we are trying to solve for the currents IE, IC, and IB with the voltages. So what are the voltages? So we are trying to solve for VCE, we're trying to solve for the collector voltage, we're trying to solve for the base voltage, we're trying to solve for the emitter voltage or the VBC based to the collector voltage. So the difference when we have design operations is that those currents and voltages are being given. So they are, we do not solve for them, they are given. So what we do is we have to establish what resistors are we going to use so that we can have those different current and voltages parameters. Okay, so in the design process, this requires a clear understanding of the characteristics of the device. Okay, so the basic equations of the network. So what are the basic equations of your network? So the relationship between IC and IB, or the relationship between IC and IE, or the relationship between IE and IB, and so forth. And then the firm understanding of the basic laws of circuit analysis. So circuit analysis plays a very important role in electronics. So if you are very good in your circuit analysis, as you can see, what we're doing here is just derived from your circuit analysis lecture. Okay, so far, what have we used? What formulas have we borrowed from your circuit analysis lectures? So we make use of your Ohm's law. So Ohm's law shows the relationship between resistance, current, and voltages. So we use the KVL, so we use your Kirchhoff's voltage law, and then we also use the Thevenin's circuit or the Thevenin's equivalent circuit. So we have also mentioned the superposition theorem. So the superposition tries to separate the DC from the AC part of our analysis. Okay, so in the design operation, since this is not the usual procedure that you're doing, the solve for IB, then solve for IC, and then solve for VCE. So this requires or the thinking process is challenged to a higher degree, because from the previous examples that we have done, from the previous derivations that we have done, it shows just a simple step-by-step solution. So in this one, we really don't have any step number 1, solve for IB. So we do not solve for IB anymore, because usually IB is given, IC is given, voltages are given. So what we are trying to solve here are the resistors. Okay, so what is RC, what is R1, what is R2, what is RB, what is RE in that case. So therefore, the path toward a solution is less defined. So we do not know what to solve first. So we are in fact contained to what is given. So from what is given, we will be starting to solve our, or to design our circuit from what is available from the circuit. So maybe it requires, okay, different basic assumptions. Okay, so we will be assuming, we will be using assumptions so that we can perform this design process. Okay, so the design sequence is sensitive to the components that are already specified. Unlike the previous circuits that we have discussed, there is a pattern really. So what is the pattern? Solve for IB first, solve for IC. So in this case, no. So it depends on what is given, what is specified. Okay, so the elements that will be determined will be dependent on what is really given on the circuit. So design operations is usually requires a higher degree of analysis, but basically they are just the same. Okay, so instead of solving for the currents and voltages, usually in here we are solving for the resistors instead. Okay, so that will be your design operations. So I have a set work here. So but since you are at the comfort of your home, so you have to try doing this, okay? So you have to try doing this, and then maybe I will be setting up a drop box, okay, for first sit work. Okay, so if you but maybe let us see if this COVID-19 will come to an end. So just visit your school book if I will be placing this sit work. I will be placing a drop box for this sit work. Okay, so this sit work is very easy. Okay, so this sit work is very easy. In this case, you have a design process. So why do you have a design process here? Because in this case, we do not usually solve for IB. We do not usually solve for IC and so on. So what we are asked here is what will be the beta, what will be the VCC, and what will be the RB. Okay, but so your IB here must be given, but this is I will just give you a value for your IB. Okay, so just visit your school book for this because this is somewhat not clear. Okay, so VCC is unknown, RB is unknown, and then beta is unknown. So given is the VCE, which is usually the one which is being asked to solve for. So what is this? 2.1 volt. So 2.1 volt here is your VE. Okay, so 2.1 volt here is your VE. So why? Because it is located at the emitter. So where is the other point here? Usually it is the ground. So if it is seen like this, so this is just your VE. So voltage across the emitter and the ground. Okay, so what is given here is your VE, your VCE. So you have your RC here, you have your RE here. Supposedly IB is given here, but this is not very clear. So I will just note here. Okay, I will place a note in your drop box in case so that you can solve for your for the unknowns. Okay, this sit work is very simple. So this is just a formula, direct substitution formulas. So relating your alpha with your IC and your IE. Okay, and then IE given your IB and given your alpha. So very simple. Okay, so you just have to look for the relationship between alpha and your beta. So I will just leave that to you. Practice. Okay, so you have to practice at home. Okay, so aside from amplifiers, so the other all of the circuits that we have discussed, all of them, if we plot them, okay, if we try to plot them and they are at the active region, so you still remember the active region, so all of them will be working as an amplifier. However, we have mentioned from the first video that transistors doesn't function only as an amplifier, although that's the main application of our BJT transistor as an amplifier. But aside from an amplifier, your transistor can also function as a switch or as an inverter. Okay, so by through proper design, your transistor can be used as a switch for computer and control applications, and also it can be employed as an inverter in computer logic circuit. Okay, so what do we mean by an inverter? So we have here an inverter circuit. So notice, okay, so notice that we have your input that is directly located or that is directly connected at your base through your RB. So take note that your RB is no longer connected to your VCC. So the VCC is only connected at the output side or at the collector side. Okay, so that's the difference between an inverter and a fixed bias configuration. So you might be wondering, this just looks like a fixed bias configuration. So no, because in the fixed bias configuration, your RB is also connected across your VCC. So we don't have a DC source across RB. Instead, we have your AC source here. Okay, so why is this AC? Because as you can see, you are trying to change state. Okay, so there are times when your input is equal to 0, other times your input is equal to 5, and then go back to 0 again, and so on. Okay, so usually the VCC here has a value which is equivalent to the source or to the input supply here. Okay, so in this case, why is it called an inverter? If you're going to look at the input and the output side, if we have no input signal here, we have an output. So the output is connected or is taken from your collector terminal. This is your output. Okay, so when your input is equal to 0, your output is equal to 5 volts or equal to your VCC, while when your input is equal to 5 volts, your output is equal to 0, and so on. So this is how an inverter input and output looks like. So for your transistor to function as an inverter, your Q point must be located, okay? So your Q point must be located at the saturation and the cutoff region. Okay, so when your Q point lies here at the active region, your transistor is functioning as an amplifier. But if your Q point shifts from saturation going to cutoff and vice versa, that is the time when your transistor is functioning as an inverter or as a switch. Okay, so the design must be properly taken into consideration for your transistor to be used as a switch or as an inverter. So what are the different considerations that we have to take note? Okay, so for your transistor inverter, the operating point must switch from the cutoff to saturation along the load line. Okay, so we have to use these basic assumptions. IC must be equal to 0, so therefore your ICEO is equal to 0. So ideally, we can make use of this, but in reality, okay, in real situation, usually ICO is of a very, very small value. So maybe in microampere range. Okay, so for a transistor to act as an inverter, when your IB is equal to 0, therefore your IC must also be equal to 0. So we are going to assume that the ICEO, what is ICEO? ICEO is the leakage current, so your ICEO must be also equal to 0. And likewise, your VCE must be equal to VCE saturation, that is equal to 0 volts. In reality, this ranges from about 0.1 to 0.3 volts, so very, very small. But for approximations or for ideal situations, we make use of VCE sat is equal to 0 volts. Okay, so when your input is equal to 5 volts, that means your transistor is on. Okay, so we're going to assume that your transistor is not just turned on, but it is heavily saturated. So how do we assure that it is heavily saturated? So that we can so we have to take down note that it is heavily saturated, so that our Q point will be lying across this saturation area here, okay, or the saturation point here. So what will be the assurance? So when your VI is equal to 5 volts, the transistor is properly turned on. So your IC sat is equivalent to VCC divided by your RC. Okay, so to satisfy this condition, your IB maximum, okay, so we have to have a maximum value of IB that must be approximately equal to your IC saturation divide by beta. So where this formula came from? So that formula came from this one. IC is equivalent to beta multiplied by IB. Okay? So that in this case, to assure saturation, so your IB maximum must be equivalent to IC sat all over beta. So this is just derived from this formula class. Okay, but the only difference is that to satisfy the condition, we will not be using a simple IB, so we will be using IB max. Okay, so how do we get assured that that is already your IB max? So your IB max must be greater than, okay, greater than IC saturation divided by beta. So in the previous examples, we have already discussed how to solve for IC sat. So when you know IC sat and then you know beta, we can determine your IB max. So your IB max must be greater than, okay? So it must be greater than IC sat divided by beta. So in this case, if we're going to go back here, so we have different levels for IB here. So if this is your load line, so this is the same load line that we have discussed previously, but if you want your transistor to operate as an amplifier, we will be choosing safe values for IB. Okay, so you can choose 10, you can choose 20, you can choose 30, you can choose 40. Okay, but if we wanted to make use of your transistor as an inverter, we will be using the maximum possible IB. And what is that? So in that case, your IB max must be greater than, okay, at least greater than 50 microamperes. So if it is greater than 50 microamperes, then your Q point will lie across your saturation point, and then that is an assurance that your transistor is working as an inverter. Okay, so that happens when your input is equal to 5. So when your input is equal to 5, our output is equal to 0. So why your output is equal to 0? Because all of the current flows across your RC. So since all of the current flows across your RC, our output here is already equal to 0 because all of your 5 volts here will be seen across this RC here. Okay, now, what if your input is equal to 0? So when your input is equal to 0, your IC is equal to 0. So when your IC is equal to 0, we don't have any drop across your RC. So since we don't have any drop across your RC here, what happens is all of the 5 volts here will be seen at the collector terminal. So we will be having an output equivalent to 5 volts. Okay? So what happens? When your input is equal to 5 volts, it is said to be saturated. So all of the voltage is across your RC, therefore our output is 0. But if your input is equal to 0, no current flowing across RC, so therefore this is 0. Where is your VCC? Your VCC is across your VC. So the output is equal to 5. So you have an inverter. But that is not always the case. You have to satisfy, of course, this following condition, okay? To make sure that your transistor is operating as an inverter or as a switch. So how does it operate as a switch? So transistor at a switch, at saturation, your IC is quite high, okay? So your IC is quite high and your VCE is very, very low. So RC sat, VCE sat, so ideally, what is your VCE sat? VCE sat is equal to 0, although in reality, usually it ranges from 0.1 to 0.3 volts. But if we're going to make use of the ideal value, so this is 0. So any value of IC sat, whenever this is equal to 0, your RC sat is equal to 0. So what do we mean by a zero resistance? A zero resistance means a short circuit. So what do we mean by a short circuit? Your transistor is operating as a switch that is turned on. Okay? So however, at cutoff, we have your VCC divide by ICEO. So ideally, ICEO is usually in microampere range. So let us say 10 microamperes. So this is very, very small. So what happens is you have a resistance which is very, very high. So ideally speaking, if we're going to assume this to be equal to 0, any value of VCC divide by 0, that will give you an infinite value. So what do we mean by an infinite resistance, class? An infinite resistance is considered as an open circuit. So an infinite resistance is equivalent to an open circuit. Therefore, that happens when your transistor is operating as a switch. Okay? So RC sat is equal to 0, R cutoff is equal to infinity. on switch, off switch. Okay? So both for an inverter and a switch, your Q point must be switching between the saturation and cutoff and vice versa. Okay? So for amplifier, your Q point lies at the active region. So that's the difference. So since we're talking about switches, there are transistors that are called switching transistors. Okay? So, why are they called switching transistors? Because they tend to switch faster from one voltage level to the other. Okay? So, we have here the time the transistor is being turned on and the time which is it wherein your transistor is being turned on. That turning on time and turning off time has something to do with the switching between the saturation and the cutoff point at your regions of operation. Okay? So, for turning on time, this is your T on. So, this is equivalent to TR plus TD. Okay, so TR is the rising time or the rise time. So that is the time. Okay, where is TR? That is the time wherein your transistor is rising, okay, or increasing from 10% to 90% of its maximum value or its potential. Okay, so TD is the delay time because even if it is turned on or you placed a supply or an input, it will not function right away. So you have a delay time. So the delay time is from 0 to 10%. So turning on time is equivalent to TR, which is your rise time, plus your TD, which is your delay time. Now, the moment you turn off your transistor or you remove the source of your transistor, the ideal response must be your transistor is turned off. However, it is not turned off right away because we still have your storage time and your fall time. So the storage time is for your transistor to fall from 100% to 90%, while your fall time is from 90% to 10%. Okay, so the sum of your storage time and your fall time is your T off time. Okay, so how fast are switching transistors? How fast they switch from one voltage level to the other, from 0 to 5 or 5 to 0 in the case of our previous example. So if we're going to compare your switching transistors versus general purpose transistor, so the general purpose transistor is one example of your general purpose transistor is the one which you are using in the laboratory, the 3N 904 or 905. Usually, this is very, very fast, actually, nanosecond. Actually, you cannot distinguish anymore if there is really a delay when we are talking about nanosecond, no? But the difference is when we're going to make use of a switching transistor, this is how fast they are turning on and turning off time. If we're going to compare this one, okay? So, for example, what is the turning on time? So the rise time and the delay time. Okay, so the rise time and the delay time. So turning on is the rise time plus the delay time. So that is equivalent to 13 nanosecond plus 25 nanoseconds. So this will give us 38 nanosecond compared to 12 nanosecond for a switching transistor. So switching transistors are really manufactured or made for these purposes. Okay, while general purpose transistor, they are being manufactured or made not for switching purposes. Okay, and likewise, your turning off time. So turning off time is your storage plus fall time. So your storage is 120 nanosecond plus your fall time is 12 nanoseconds. So that will give you 132 nanosecond. So turning off is 132 nanosecond. Although 132 nanosecond is very very fast, your naked eye cannot notice that anymore. But if we're going to compare that with the switching transistor, the turning off time is just 18 seconds. So 18 seconds versus 132 nanosecond. So they are really fast switching transistors. Okay? Troubleshooting techniques. So when you're at the laboratory and then your circuit is not quite functioning well, so how would you know? If you have a correct data when you're performing these experiments at the laboratory, so this troubleshooting techniques might help you. Okay, so it is said that for an on transistor, when your transistor is turned on, the voltage VBE, so when you place your voltmeter across the base and the emitter terminal, you should read a voltage which is within the neighborhood of 0.7. So not exactly equal to 0.7 but nearing 0.7. So in practical application, maybe you can read about 0.5 or 0.6 volts. So if that is within the vicinity of your 0.7 volts, so therefore your transistor is good. Okay, but if it is not, so maybe there is a problem. So you need to troubleshoot it. Again, for a typical transistor amplifier in the active region, VCE is usually about 25% to 75% of your VCC. Okay, so when you compute for your VCE and then your VCE is within 25 to 75% of your VCC, then your transistor is typically functioning as an amplifier. If it is below 25% of your VCE, so it is nearing the cut-off region already. So you have to consider that. Or if it is nearing more than 75% of your VCE, so it is nearing your saturation already. So for us to be assured that it is still within the active region, so your VCE must be within 25 to 75% of your VCE. Okay? So troubleshooting process is a true test of your clear understanding of the proper behavior of a network and the ability to isolate problem areas using a few basic measurements with appropriate instruments. So you have to test for this value. Okay? So for example, you are measuring your IB and then you find out that your IB is greater than your IC. So you must think already, because in our lecture IB is always smaller compared to IC and your IE. So maybe there's a problem already with your circuit. So you have to know the basic. Okay? Not just get the data and then you just when you read a value, you already accept the value. So you have to look at the validity of that values. Okay, and of course experience is the key. So you need to perform more laboratory. However, this COVID-19 is really giving us a hard time in performing your experiments, but just practice using your multi-sim. Anyway, the answers are just the same. So you just try performing. So if you have excess time, you create from your multi-sim. You build your fixed bias configuration. You build your emitter stabilize, and then try computing or try measuring those values. Okay, so if you want to compute it, uh, and then afterwards you create that or you build that using multi-sim, and then compare your computed value from the results that you will be measuring using your multi-sim, so that at least you can see if there is a relationship between the computed value and the actual value in the multi-sim. Okay, so these activities can be made at home. Okay, so at the safety of your own home. So based on the readings provided in the figure, let us determine whether the network is operating properly. And if not, what must be the probable cause? Okay, so look at here. So we have here, our supply is 20, and we can read at the collector side that this is also 20. So if your VCC is 20 and your VCE is equal to 20, so that only means that no current is flowing across this one. Therefore, you have no IC. Okay, so you don't have any IC here. But also here, so all of the 20 volts is being placed here. So 20 minus 19.85. So if we have here 20, so if we have here 20 volts, your VCC minus 19.85 volts. So that means you only have what? Around 0.15 volts remaining. Okay, so we all know that 0.15 volts cannot turn on your transistor. Why? Because for your transistor to be turned on, your VBE must be equal to 0.7, right? So the only remaining value for voltage is just 0.15 because all of the 19.85 is being dropped at your RB. So therefore, why do we have why don't we have IC? Maybe because your transistor in the first place is not turned on. So maybe there's a problem with the transistor. There's no problem with the source. Why? Because we can read the 20 volts. So maybe the defect there lies on the transistor itself. Okay? So another thing is, hey Google, turn on lights. Okay? So
turning 3 lights on.
So we have here the second circuit. So the second circuit is we have 20 volts here. So we have 20 volts here, and you read 4 volts across your base. So if we have 4 volts here and your emitter voltage is 3.3, so we have VB. So you have your VB is equal to 4 volts and your VE is equal to 3.3 volts. So when your VB is equal to 4 volts and your VE is equal to 3.3, so we have a VBE here which is roughly around 0.7. So if it is 0.7, therefore your transistor must turned on. Okay, must be turned on. However, there is a problem here because at the collector, we read 20. So therefore, IC is not being considered here because supposedly if this is 20 and this is also 20, we have no drop across 4.7. So if we don't have a drop across 4.7, that means we don't have IC. So in this case, since IB is functioning well, okay, we have VE here, this is functioning well, maybe there is just a loose connection. Maybe your RB here is not your RC here is not connected properly with the collector terminal. So unlike in this first case, there is really a problem with your transistor. Okay, so that is how somehow you troubleshoot your circuit. Okay, so look at the specific value. And also look at this one. So VCE. Okay, so that is how. So we say that VBE must be equal to 0.7. So 0.7 was not properly observed here, while 0.7 was observed here. So here, the problem only lies at this point because this is functioning well. Okay? So aside from that, we have the bias stabilization. So for DC analysis, we are establishing the stability of your system. And we have so far concluded that the most stable among your configuration is the voltage divider configuration. Okay, so in DC analysis, always remember that we do not discuss yet the amplification factors, but we are assuring that your Q point is lying at the active region. If your Q point is not at the active region, if it is switching between your saturation and cutoff, therefore, your transistor is functioning as a switch or as an inverter. Okay? So, the stability of a system is a measure of the sensitivity of a network to variations in its parameters. Okay? So, there are three parameters that affects the stability of your system. So what are those? So you have beta, wherein your beta is not a fixed value because it says here your beta tends to increase with an increase in temperature. So when you use your transistor in a circuit, the tendency is your circuit to heat up, so that means increasing in temperature. So your VBE actually it's not just equal to 0.7. So VBE likewise is affected by temperature. Okay, so all of them actually is temperature dependent. So your VBE decreases about 7.5 millivolts per degree Celsius increase in temperature. And lastly, your ICO, which is your reverse saturation current, which doubles in value for every 10 degrees increase in temperature. Okay, so this is a table showing the variation of a silicon transistor parameters when with temperature. So your ICO or your reverse saturation, your beta, and your VBE. Okay? Your ICO, so the stability factor S, so this is just a formula class. So ICO is the change in collector current with respect to the change in leakage current. VBE, that is the change in the collector current with respect to the change in your VBE. And then stability factor of beta is the change in the collector current with respect to the change in beta. So since your leakage current, your VBE, and your beta is changing with respect to the temperature, so as your collector current. So the ratio between their changes is your stability factor. So networks that are quite stable and relatively insensitive to temperature variations have low stability factors. So if you're going to choose between two transistors and their stability factors are given, so look at the one which has a lower value. A lower value of stability factor will be give you a quite stable circuit, and it is relatively insensitive to temperatures. Okay, so since the three of them are connected, okay, so why are the three of them connected? Because, okay, if we change beta, so if we change VBE, what affects VBE? So if we change VBE, IB will be affected. Why? Because usually IB is VCC minus VBE. Okay? So changing VBE, so you have here, for example, IB. So changing VBE changes your IB, affects your IB. Okay? But when IB is affected, IC is beta multiplied by IB. So indirectly, VBE has nothing to do with IC, but VBE has something to do with IB, and IB has something to do with IC. So therefore, we have to consider that. Another thing is beta. Beta is very obvious. Why? Because IC is beta multiplied by IB. So if beta changes, so as your IC. Okay? And also, your IC is composed of two things. Your IC majority plus IC minority. So IC minority are your leakage currents or your ICO. Okay? So if your ICO increases, so likewise IC will be affected. So all of those three is being reflected to to your IC. So therefore, if all of them changes with respect to temperature, either increase or decrease with respect to temperature, it has something to do with your IC. Okay, so therefore, IC is equivalent to the sum of your stability factors multiplied by your changes in beta, changes in VBE, and changes in your ICO. Okay, so lastly, we have here an assignment. Okay, so I will be again placing a drop box in your lecture so that you can do your assignment. Okay, so all of this will be taken up. You can review your PowerPoint presentation, so you can rewatch the video. If you have any question, you can message me or you can comment on the video so that I will try to answer your question. Okay, so try solving the set work a while ago and then the assignment here. Okay, so I will be placing a drop box in your school book depending on the latest development on COVID-19. So let us see. But just visit your school book every once in a while so that you can look for the deadline. Okay? Anyway, I'm not very strict with the deadline, although I am placing a deadline there. If you cannot comply with the deadline, all you have to do is to send me a message and then you just attach your answer to the message. I just want to see who complied with the date, although I will be accepting late papers. Okay, so there will be a deadline, but I will still be accepting late sit works and late assignments. Okay, so that will be it for our DC analysis. So no amplification yet for DC analysis. We're just establishing your Q point. Okay, so what is the importance in DC analysis? We are trying to look for the most stable configuration, and that is your voltage divider configuration. Okay, so that's it. So the next videos will be about AC analysis. So AC analysis, there we can witness already what do we mean by transistor amplification. Okay, so just stay safe at home. Try reading your books. Okay, so all of this, try reading your books, try solving problems at the end of the each chapter, so that you can practice, so that when we come back to school, you'll have series of exams. Okay, so have a nice day and bye.